Well, let's just make this the last video, and then we can move into all of our tests. Our divergence and integral tests, comparison tests, alternating series tests, the ratio tests, the root tests. Lots of tests. And that's why we're learning all this stuff, so we can start to test some things. Let's go. Now, we've got to talk about some properties. And you're like, no, another theorem, and there's so much writing, and it looks like hieroglyphs. What is this? Well, let's talk about it. So, first one, we're going to say, suppose that our sum of some a sub k converges to a number, big A. Maybe it's 5. And then it talks about, we got some real number c. So we're saying if you multiply the real number c times a sub k, and we know the sum of a sub k converges, well, can't you just take the c and take it out to the front? And then it's just multiplying some c times whatever it might have been, that big A. We're saying just because you're multiplying by a constant, you're good to go. You're good to go. Right? So maybe the sum of 1 over k squared as k is equal to 1 up to infinity converges. Well, I could make that a 10 over k squared. It's still going to frickin' converge. We're just multiplying it by 10. So, I don't know. Take it or leave it. There's our first one. There's a lot of the same rules we learned in, what was that? Improper integrals? It's actually the exact same thing. It's the same thing. Yeah, it's the same thing. All right, now let's suppose that our sum of a sub k diverges. Well, if you add a constant to it, it's still going to frickin' diverge, just as long as that c isn't 0. What's infinity times 4? It's infinity. What's does not exist times 12? What? Doesn't do anything. So if the sum diverges, I don't care what constant you multiply by, as long as it's not 0, it's still going to frickin' diverge. Next. So we're going to say we got a sum a sub k, and that's going to converge to a. And then we got a sum b sub k, and that converges to b. So we're saying if you want to add or subtract these, it's still going to frickin' converge. Because if this is going to a number A and this is going to a number B, let's say A was 7 and B was 5. Could you do 7 plus 5? Is it going to become an infinity? Nah. So a lot of this wording seems crazy, but they're not concepts that are nuts. If it converges to a number for an A and it converges to a number for the B, add or subtract those freaking numbers. So the sum or the difference will still converge. Now next, where we said if a sub k converges and b sub k converges, then we know that the sum or the difference is going to converge. This is a little different. So let's suppose one of them diverges and the other one converges. We're actually going to get to a number for b sub k. For a sub k, we're going to get infinity. So we're going to say that the sum of those two, the two sequences inside of the series by added or subtracted will also diverge. What's infinity plus 5? Still infinity. What's 5 minus infinity? Negative infinity. It doesn't make any gosh darn difference. Or how about does not exist plus 12? It still doesn't freaking exist. And then we have our last one. So if m, big ol' m, is a positive integer, then the sum, if it starts at 1, and the sum, if it starts at m, say m is 12. Dude, it doesn't really matter where you start. Either both of them frickin' converge, or both of them diverge. Whether we start k at 1 or we start k at 12. If they both converge, or if one converges, the other converges. If one diverges, the other one will diverge. Because infinity is a big-ass number. Oh, wait, infinity is not a number, it's a concept. And if we're taking these sums to infinity, I don't care about the first couple of terms. It's not going to make any difference. So there is our initial game. We got these rules. So we want to use some of these properties in order to solve. So let's try this. Oh, goodness. So we have a difference going on here. So let us use one of our properties where we know, we're like, wait, we're going to use this. But we're going to go backwards. We're going to subtract, and let's solve them individually. And if we find out one of them diverges, the whole thing diverges. If we find out both of them converge, then both of them converge. And I think on this one, we're going to be able to actually solve. So what do we got here? What do we got here? So this is equal to the sum is k is equal to 2 up to infinity of 1 over 3 raised to the power of k. What? Sorry, this is 1 to the k also. And the sum is k is equal to 2 up to infinity of 2 over 3 to the k plus 2. Can't play that same game by throwing a k plus 2 up there because, well, I don't know. I don't know what's going on. All right. But I'd like to do one more thing. If you don't mind. Wait a second, I wrote my problem in wrong. I'm sorry. I want this to be 1. Sorry, my bad. And let's do one more thing. Let's use the constant multiple rule. Let's take that out to the front. Hey, there we be. So we just brought our sum in, messed around with it a little bit, and let's see what we do. Now, both of these are geometric series. And the ratio for both of them is going to be 1/3. But let me take it just a step further. I try to do too much. K is equal to 2 up to infinity, 1 over 3 to the k minus 2 times the sum is k is equal to 2 up to infinity. And there's a reason why I yanked that too. Because now we can call this 1/3 to the k plus 1. Because you can call 1 any freaking power you like. There we are. So now, what do we have here? Now, this is where it's going to get freaking nutty. But hopefully, you've messed around with a few of these problems. So let's deal with them individually. I want to use just the first one. So this is not an equal sign. I just want to check it out. And I just want to write down some stuff. So this is 1/3 squared plus 1/3 cubed plus 1/3 to the 4th plus 1/3. Okay, do you get it? Okay, let me just stop there. I think that's probably good enough. So we need to figure out what our A is. It's right here. It's your first term. That's 1/9. So for this, we're going to write down our A is equal to 1/9. But what's our R? Come on, dude. It's sitting inside of here. R is equal to 1/3. Oh. Okay. Well, I think we can solve that pretty well. And again, we are just dealing with R first. So we can look at this and we can evaluate it. Let's evaluate. The sum is k is equal to 2 up to infinity of 1 over 3 to the k by using that this is 1/9 over 1 minus 1/3. So what is this? 1/9 divided by 2/3. What's that? 3 over 2 times 9. We get 1/6. We get 1/6 for our first. Okay. But now we need to subtract out. Oops, let me color code. We need to subtract out our second. So let's look at this one. Let's figure out what we get. All right, let's go check it out. And we write it in blue to separate it out. So k is equal to 2 up to infinity of 1 over 3. And I'm not adding in the 2. We know how to multiply by 2, don't we? So let's write out some terms. You'd be like, all right, so this is 1/3 to the 3rd plus 1/3 to the 4th plus 1/3 to the 5th plus ... All right? So there's our A. Our A is always the first term. So we have 1 over 27. What's our R? It's the thing inside. It's 1/3. Thus, we can solve again by using the... Oops, let me move this down. I missed it. All right. So now we can go through and solve for this. What do we have? So this is equal to our A, our 1 over 27 divided by 1 over 1/3, which is going to be 1 over 27 divided by 2/3 one more time. So we have 1 over 27 times 3 over 2, thwack, thwack. We get 1 over 18. So there is our second sum. So it turns out that this is merely equal to 1/6 minus 2 times, don't forget the 2, the 1 over 18. So what do we have? We have 1/6 minus 1/9. So this is what? Sorry, cheating. 3 over 18. 2 over 18. We get 1 over 18. It converged. Dang, all these videos are so gosh darn long, and I'm not even done with the next problem. But don't worry, the next one's shorter. Okay. Now I ask you about this one. Does that thing converge? Does it diverge? Well, let's just check it out. Let's go. This one's quicker. I want to bring this in. I want to bring it in, use our sum rule. 5 times 2 over 3 to the k. Hey, we know that one converges. That's good. That's good to go. K equals 1 to infinity of 7 to the k minus 1 over 6 to the k. Okay. Now, we look at this first one. We have 5 times. It's taking the constant out. The sum is k is equal to 1 up to infinity of 2 over 3 to the k. That will converge, right? That'll converge. We can deal with that later. Now let's manipulate this one out a little bit. I don't like this 7 to the k minus 1 over 6 to the k. That bothers me. Did you know that this is 7 to the k minus 1 is 7 to the k times 7 to the k to the negative first all over 6 to the k? So this is actually equal to, come on, pen, work. Sorry, this is this weird thing. So this is actually 7 to the negative first power times 7 to the k over 6 to the k. Wait a second. This is 1/7 times 7 over 6 to the k. So let's rewrite that. Wait a second. What's our r? Uh-oh. R is greater than 1. 7 over 6 is greater than 1. Therefore, that diverges. So if one piece diverges, the whole thing diverges. Therefore, the whole sum diverges. All we have to do is find one piece that diverges, and we can say the whole gosh darn thing diverges. So that's why I looked at this thing. Well, I also know the answer to the problem. But I'm looking for something to diverge. I'm not looking for convergence. I'm looking because once we find something diverges, we can end the problem. Now, please don't throw Hail Marys and just be like, diverge. You better show me why. You better tell me why. We got to know. You can't just state that it diverges. You got to tell me why it diverges. So this can occur. Yeah. And again, long video. My apologies, but we are done with 10.1, 10.2, 10.3. All the stuff to build us up to be able to do everything in the future. So this is quote-unquote review. But I imagine it's not review for most of you. I know it wasn't review for me. So, all right. We will get into all of our series tests soon. I will see you then.